time only? I see Tyler, like somebody else also. Click on more and see people, participants here. So we have 2 people with us here. Okay.
Oh, I thought you were fine for
It opened the 1st of May, but I was like, I can't.
Oh, wow. Just remember, I only did this.
Okay, I think it is time to start. So a new chapter, and probably the last chapter that contains standard electromagnetism. So what is following is going to be based on what we covered so far, but it is going to require a good amount of confidence, especially when we're talking about RCL circuits and electromagnetic waves. So let me summarize where we stand from so far from with this chapter, with the chapter related with magnetism. So we started the study of magnetism by describing how electric charge reacts to the presence of magnetic field. And we said that if this electric charge is in motion, it feels force that we call magnetic force. And the magnitude of that magnetic force is proportional to the magnitude of the electric charge, proportional to the speed of that electric charge, proportional to the strength of the magnetic field. And there is a factor describing the direction of motion of the electric charge with respect to magnetic field. And here the angle theta is the angle between the velocity vector and the magnetic field vector. So integral part of this equation, this is, by the way, called Lorentz law. Integral part of it is the right-hand rule, the first right-hand rule. The first right-hand rule gives you the direction of the force that this moving charge experiences. So as a result of this Lorentz's law equation, we brought a similar expression for the case when instead of a single moving charge, we have a stream of charges forming a current. So when a piece of wire with current in it is in magnetic field, a similar force appears, and the value, practical value of that expression comes from the fact that electric motors rely exactly on this force. So when a rectangular frame is in motion in external magnetic field created by, let's say, permanent magnets, for example, that rectangular frame is subject to a torque, which rotates it, and you have electric motor created with the simple means. Unrelated to this Lorentz's law, we had equations that describe how electric currents themselves create magnetic fields. And for the case of electric current flowing in a long piece of wire, straight piece of wire, we said that magnetic field created by that current is proportional to the current and inversely proportional to the distance from the current. And again, part of that expression is another right-hand rule which describes the direction of the produced magnetic field. Well, another magnetic field created by a current that is flowing in a solenoid, in general, a long solenoid with multiple turns like this, usually circular shape. The magnetic field inside that solenoid is almost uniform if you are far away from the ends of the solenoid inside here, and it is given with mu naught times N times the current. And here is the number of turns per unit length of the solenoid, per unit length, this in this direction. Again, important part of this equation is the right-hand rule, the second right-hand rule. And this right-hand rule is tricky to apply because usually on the screen, figuring out the direction of the current in this three-dimensional solenoid is not that trivial. And you have to know the direction in order to apply the right-hand rule appropriately. Usually we're interested in the magnetic field inside the solenoid rather than anywhere else. Okay, so any remarks so far about those two stories? Now, of course, the magnetic field created by two different shapes is not sufficient because the shape of the wire with current can be any shape you want, right? It could be something different from a straight wire or solenoid with multiple turns, right? It could be anything you want. It could be something like weird. And the question is, how do you describe the magnetic field created by currents that are flowing in wires with arbitrary shape? And the answer was given with Ampere's law, the third Maxwell equation, which is tricky to write without using notations of calculus, but it basically looks like this. If you have some currents, let's say here, a current flowing this way, current I1, a current flowing maybe this way, current I2, and you want to figure out the magnetic field created by multiple currents flowing in wires with arbitrary shape, what you have to do is you have to imagine a closed curve, appropriately chosen closed curve, arbitrary shape but closed curve. And after that, starting by taking small pieces of this imaginary closed curve, you can calculate the parallel component of the magnetic field around this small piece with length delta L, small piece of the closed curve, multiplied by the parallel component of magnetic field, and going to multiple pieces with length delta L, adding the products is going to give you a result that is equal to magnetic permeability of air or vacuum multiplied by the total current that pierces the plane defined by this arbitrary shaped imaginary curve. So if those two currents pierce the plane defined by this imaginary curve, the total current is algebraic sum of I1. Well, in this case, I2 is in opposite direction, so probably it has to be taken with negative algebraic sign for this particular case on the board. So this is Ampere's law, complicated to write without using more sophisticated notations, but this is what this Ampere's law is what we use to derive this or this. Now I have to make a remark that Ampere's law has to be supplemented by a small corrective term, which I'm not going to write. I just will put it as a rectangle there. Because in most cases, this additional term called displacement current term, for most cases, it has small numerical value compared with the rest of the terms in the equation. So in most cases, it can be neglected. And since it is not, the displacement current is not analyzed in our textbook, I'm not writing it. But now we have 3 of the 4 Maxwell equations. So the first Maxwell equation was Gauss's law, which says that the electric flux that goes to arbitrary closed surface is equal to the total charge, electric charge enclosed by that surface, divided by electric permittivity of vacuum or air. The second Maxwell equation says that the magnetic flux that goes to arbitrary closed surface is 0. So this second Maxwell equation also can be expressed with a sentence. So the second Maxwell equation basically says that no magnetic monopoles exist. Right? If magnetic monopoles existed, the second Maxwell equation would read total magnetic poles enclosed by the surface divided by some constant number or multiplied by some constant. But we know that magnetic monopoles don't exist. Magnetic charges are always plus and minus together, north and south together, glued to each other. And as a result, any surface that any closed surface encloses equal amounts of pluses and minuses, equal amounts of north and south poles, and the net enclosed magnetic charge is 0. And this is what the equation says. So keep in mind that magnetic flux through any surface is defined in a way similar to electric flux, right? The definition for electric flux was something like this. Electric flux through certain area A was defined as product of the area multiplied by the electric field through this area, piercing this area, times cosine of the angle between the electric field and the normal to the area, normal, perpendicular to the area. In a similar manner, the definition for magnetic flux is magnetic flux always through certain area is area multiplied by magnetic field multiplied by the cosine of the angle again between the magnetic field and the normal to the area, the perpendicular to the area. Okay, so now we have the first, the second, and the third Maxwell equation. For full description of all electromagnetic phenomena, we need the last Maxwell equation, the fourth Maxwell equation that we're going to write today. So keep in mind that those four equations are sufficient you to design any electric or electronic device. Not only sufficient, but they are necessary. You cannot design the chips in this computer if you don't have full understanding of how the four Maxwell equations work. So the last Maxwell equation is called Faraday's law, and it is a numerical description of a very simple phenomenon. So if you take any piece of metal conductor, and you move it in magnetic field, the experiment shows that voltage is generated in this piece of metal, moving metal. Actually, what you need is a relative motion between external magnetic field and the piece of metal. So basically, if I take this piece of metal and start moving it in the magnetic field of the planet Earth, there is a voltage difference between the two ends of this piece of metal. Well, of course, you may doubt that this is the case, but I can show it. Well, instead of moving a piece of metal that is this wire, let's move multiple pieces of wire just to generate sufficient voltage between the two ends of this coil. So here it is. I'm going to connect this sensitive voltmeter, ammeter in this case. Here it is, to the coil. This. Let's do it. This. And so this is sensitive ammeter, and now I have a closed circuit. And if I have a relative motion between the magnet and the coil, here it is, you see that a current flows in this closed circuit, therefore there is a voltage that drives this current. So this phenomenon is called electromagnetic induction. And the numerical description, how many volts is the induced voltage in this closed circuit, is called Faraday's law, and this is what we're going to write in a minute. So keep in mind that as simple as this phenomenon is, the entire, almost all of the electric power industry is based on this. So you have some permanent magnet or electromagnet, it doesn't matter, but some magnets, and you have somebody moving the magnet with respect to a coil. The result is a voltage, induced voltage. That voltage comes to your homes. It comes to the grid. So all electric generation, except, what is the exception? Is there alternative way of generating electricity, except with this relative motion? What? Well, are you going to do the motion in a circle, or this way is easier for me, but in general, if I do a circular motion, it's going to do the same thing. It's just going to be more difficult for me to generate it. But, well, all electric generation except the photovoltaics, except the solar panels. Solar panels are the only other way to generate electricity, different from Faraday's law of electromagnetic induction. Okay, so let's figure out how does this Faraday's law work. And well, instead of analyzing the relative motion of a very complicated coil, I'll take a single piece of coil, a single loop, metal loop with rectangular shape. And instead of this complicated magnetic field created by a bar magnet, think about uniform magnetic field everywhere in space right here, into the board, uniform magnetic field into the board. So, and now instead of moving the entire rectangular piece of wire, let's move only one piece right here, this movable piece right here. So you just move this side of the rectangle with speed v. To the right in this case. Let's see what happens in this case. Well, the experiment shows that now you have this closed circuit, and the experiment shows that current is going to be induced in this circuit. Voltage is going to appear suddenly, and you're going to have current flowing because you have a closed circuit, a closed piece of metal. But how exactly it happens? It is, well, one way to look at it is to look at it from the point of view of Lorentz forces. So remember that Lorentz force appears when electric charge is moving in magnetic field. Well, this piece of wire that is in motion has electric charges in it. And the negative electric charges, the electrons, are free to move. So any force, Lorentz force, is going to move them. So let's figure out in which direction those electrons are going to move if this piece of wire is moving to the right. The first right-hand rule says thumb of your right hand in direction to the velocity vector. Magnetic field, the fingers of your right hand, and the magnetic force that is going to appear acting on positive charges would be this way, out of the palm of your hand. Well, electrons are negative, so the electrons are going to move in opposite direction, and they're going to accumulate on the side of the moving piece of wire. Uncompensated positive charges are going to be left on the other end of this piece of wire. So, in other words, the conventional direction of the induced current when this piece of wire is moving to the right is going to be this way. So the current I is going to be flowing this way. Well, let's keep it here. We can even calculate the voltage difference between this and this end of the moving piece of the moving piece of wire. The voltage difference between those 2 points. Well, how? Well, use Lorenz's law for the magnetic force that acts on the charges in this moving piece of wire. So that magnetic force is going to be equal to the magnetic force that acts on a charge Q is going to be proportional to the charge, proportional to the speed of the charge, and the speed of the charge is practically the speed of motion of the piece of wire, this V, proportional to the external magnetic field magnitude B. Now you have sine of the angle. So this is the angle between the magnetic field into the board and the velocity vector to the right. That angle is 90 degrees. Sine of 90 is equal to 1. So I'm not going to write a factor of 1. So this is the force that separates positive and negative charges. Negatives go down, positive left up. Now look, on the other hand, if you have positive charge, electric charge here, negative electric charge here, you have electric attractive force, Coulomb force, attractive force that wants to put them back together. The value of this attractive force is the electric field between this and this end. F electric is electric field multiplied by the value of the charge. Electric field here, where we mean the electric field between this and this end of the moving wire. In other words, this is the electric field coming out of plus into the negative charge. So when the straight piece of wire is moving to the right, you have an equilibrium between those two forces, right? The magnetic field force tries to separate the charges, plus from minus, while the electric attractive force wants to put them back together. So you have certain equilibrium. In other words, they become equal to each other. So you have this electric field times charge becomes equal to charge times speed times magnetic field. You can cancel out here the charge, Q. And now, well, electric field is good, but our measuring devices easily measure voltage difference. So let's switch from electric field between this and this point into voltage difference between this and this point. So if those 2 points are separated by the length L, the length of the wire practically, you have that electric field is equal to the voltage difference. Instead of delta V, I'll write it just as V, even though it is a bad style, it is easier. Voltage V divided by the step size, the distance between those 2 points is distance L. Magnitude of electric field is this. So substitute that electric field here, and you have voltage difference capital V divided by the length of the wire is equal to the speed of the moving wire multiplied by magnetic field. In other words, the voltage difference, the induced voltage difference between the 2 points, the 2 ends of the moving piece of wire is equal to the speed of the wire multiplied by the magnetic field and multiplied by the length of the wire. So very simple, but very useful result. So let's get one piece of wire. according to this equation, well, I don't have the rest of the rectangle, but even this straight piece of wire in motion in magnetic field of Earth creates voltage difference between this end and this end. And I can connect a light bulb, probably is not going to be bright enough to, but I can connect those two ends to LED light, and when I'm moving, you're going to see that the LED lights are going to light up. And we're going to see it next time on Friday. In one of the homework assignment problems, you have exactly the same situation. You have the wings of an airplane. So imagine that those are the wings of the airplane moving in the magnetic field of the planet. What is the voltage difference between this end and this end? You can calculate it if you're given the strength of the magnetic field. It has to be perpendicular to the direction of the motion, but you can arrange that. And the wings have to be appropriately oriented. But in general, this formula predicts a result that you can easily measure. You can measure the voltage and the current that voltage difference creates very easily. Any remarks and comments and questions and issues, anything that comes to mind here? So our bodies are not made of metal, right? But our bodies are still conducting electricity. So if you're moving very fast in the magnetic field of the planet, also voltage difference is going to be generated in your body, current is going to flow. Luckily for us, well, you have to move very fast in order this current to be to matter at all. And or the magnetic field in which you're moving has to be much stronger than Earth's magnetic field. And you are, of course, you have to move in the direction perpendicular to the magnetic field lines. In other words, well, small effects usually sometimes have visible biological effects. So, okay, now the next step. Well, look, this expression that we derived for the voltage induced. We call this voltage induced voltage, and I'll use the term induced voltage. I'll put a subscript induced. But in the textbook, instead of induced voltage, they call this induced voltage electromotive force. Electromotive force. But this is old notation. In reality, this is nothing else but voltage. Voltage induced due to the motion of a conductor in magnetic field. So sometimes I'll say electromotive force, sometimes I'll say induced voltage. Probably just using induced voltage is less confusing, but we still have to use the terminology in the textbook. This equation that we derived is a manifestation of Faraday's law. But you can generalize this result for the case when, instead of a moving straight piece of wire, you have arbitrary shaped wire moving in magnetic field. And this is going to be our next task. Generalize this expression for the general case of a moving conductor in magnetic fields. Well, we're still going to do the analysis using the same rectangular piece with one of the sides of the rectangle moving to the right with speed v, and the magnetic field into the board. So let's still use this, but now rewrite this result the following way. So introduce a coordinate system with x-axis to the right, the origin of the x-axis probably here at this end of the rectangle. And let's say that in time interval delta t, the moving side of the rectangle goes from here to here. So in other words, the moving side of the rectangle covers a distance delta x in time interval delta t. So delta x, of course, is x final minus x initial. So x initial is this length. So this is x initial. X final is this length. Here. X final. X final. Now, in our formula for the induced voltage, just rewrite the speed in terms of distance divided by time, right? It is delta x divided by delta t in state of velocity magnitude times magnetic field times length. Now, delta x, we said, is final position minus initial position. So it is x final minus x initial, all of this divided by delta t, and all of this also multiplied by v and l. And now just rearrange those factors. So write this as x final times L times magnetic field minus x initial times L times magnetic field, all of this divided by the time interval delta t. And now look what happens now. The product of x final times the length of the moving piece of wire. So here is x final multiplied, so here it is, multiplied by this length gives you this final area of the rectangle. I just will call it area final. So this is area final times magnetic field. Similarly, x initial is this length multiplied by L gives you this area, which I will call area initial, A I. T. And now look what you have. You have area multiplied by magnetic field that pierces this area. This is exactly the magnetic flux to this area. The angle in this case is the angle between the area, the perpendicular to the area is into the board, the magnetic field is also into the board, so the angle is 0, cosine of 0 is 1. So it is just the magnetic flux. So this is magnetic flux on the final moment of time. This is magnetic flux at the initial moment of time. So magnetic flux final This is magnetic flux initial. And therefore, you can say that induced voltage is equal to, well, final minus initial, we usually denote with a delta. So delta magnetic flux divided by the time interval delta t. Well, I'll insert here a minus sign, and we're never going to use this minus sign directly. But for consistency of the four Maxwell equations, this minus sign is needed. And also this minus sign can tell you the direction of the induced current in your moving piece of metal. If you know how to use the rules of vector calculus. Since we don't want to go into calculus, we're not going to use it. Instead, we're going to formulate a verbal rule to figure out the direction of this induced voltage, induced current. So we're going to do that next time, hopefully. Now, the way we have this expression here, this expression says that induced voltage is equal to the rate of change of magnetic flux through the area defined by your moving coil or piece of wire, or relative motion is what is needed actually. The wire may be stationary, the magnetic field could be in motion. Okay, now this equation is the fourth Maxwell equation. It is called Faraday's law. And the beauty, even though we derived it from the previous equation that was valid for a rectangular loop with one side only moving, this equation, we lost all information about the shape of the coil, about what is moving. So all of this was lost. And this equation now, it can be shown that this equation is valid for any shape of conductor in relative motion to any magnetic field. So this is the beauty of the Maxwell equation written in this form. It is valid for arbitrary shapes and arbitrary magnetic fields. So once we have Faraday's law, we have a complete description of the Maxwell equations, and we can start thinking about different conceptual questions. In case if you any remarks, questions, any thoughts that come to mind. If not, let's look at some conceptual questions. Let's look at probably conceptual question like this. So for people that are online, they cannot see this particular slide, but I'll try to describe it. So the slide shows exactly what we have here on the demonstration. You have some conductor in a shape of a coil. Let me make it a bit larger. So you have a coil like this, connected to ammeter, and you have a piece of permanent magnet bar shaped. So the question is, how do you change the magnetic flux? Move the magnet down, drop it in other words, or move it up, or move it sideways. Now, you see the magnetic field lines, the blue lines. How do you change how many magnetic blue lines intersect the area defined by this circular coil? Well, any way you move the magnet, it is likely that it is going to create some change of magnetic flux. Of course, the largest change of magnetic flux, the fastest rate of change is going to occur when you are moving up and down, as you see from the experiment here, right? From this demonstration. You need a strong magnetic field in order to notice any change of magnetic flux if you are moving this way, just because the magnetic field on the sides of the bar magnet is very small, but it is there. You can, with a big magnet strong enough, you can see induced current when it is moving even this way. But it is much easier to see it when it is moving this way, just because the rate of change of magnetic flux in that case is fastest. So let me see if the next question, if we're equipped to ask and figure out. In order to change the magnetic flux to the loop, what would you have to do? So they're offering you either change the orientation of the loop, or change the loop area, maybe by squeezing it, if you have this thing to squeeze this. Thicker wires probably too much, right? We're only talking about the flux to the area defined by the loop. So 1 and 2 seem to be working for changing the magnetic flux, and 3 not working. That's, yeah.
What does tilting the loop do?
Well, tilting the loop is going to change the orientation of the magnetic field of those blue lines. So you see, you have in the definition of magnetic flux, you have cosine of the angle, right? The magnetic flux, if the angle is like this, the flux, air flux is 0, right? So there is a directional dependence. So tilting the loop is equivalent to doing this. You have high air flux now. You have 0 flux going through the plane of the paper.
So is this saying if the magnet were to still go up and down or sideways, but you were to tilt the loop, say from this to this?
It also changes the flux, yeah. Well, we're talking only about relative orientation. You see that this is what happens. Huh. Let's see the next one. Huh. Oh, I see. They have done it as an animation, and you have multiple things. So you see this cosine, it describes the mutual orientation. Okay, so next time, we're going to talk about how to figure out the direction of the induced current in a closed loop where you have induced voltage. So this direction is going to be described with kind of complicated rules called Lenz's rules. So please start working on this chapter, start reading this chapter, because what follows, the sections about mutual inductance and self-inductance are going to be tricky. Well, the most important part of the material is in what we said today. But the tricky questions that come from Lenz's rules and from our definitions for inductance and mutual inductance, those are going to be a little bit tricky, but they're going to be needed later on when we talk about RCL circuits. So we're going to continue on Friday. Get ready for other questions on the screen.